Hello, and welcome to my lecture, part of the Growth Astronomy School on Observational Techniques for Transient Studies. I'm Daniel Perley from Liverpool John Moores University, a partner in the Global Growth Collaboration. GROWTH stands for the Global Relay of Observatories Watching Transients Happen, and we are an international team of astronomers that have joined forces to explore the dynamic universe using telescopes around the globe, spanning the electromagnetic spectrum and uninterrupted by daylight. When dealing with so many different telescopes and different types of telescope, a broad and practical understanding of data acquisition, reduction, and analysis is essential. In this lecture, I will introduce you to the fundamentals of image data reduction for optical astronomy. Optical imaging is one of the simplest and most intuitive types of astronomical observation. After all, each of us carries around two optical imagers of our own, but it is no less important. This will be one of three lectures related to optical imaging, the others being a lecture on photometry by my LJMU colleague Chris Copperwheat, and a lecture on image subtraction by Christopher Fremling. Why take optical imaging in science? There are many reasons why we may want to record an image of some part of the sky. One might be discovery, to look for something new or interesting, such as a new supernova in a galaxy, as shown here. Another would be photometry, to measure the specific brightness of a known object, perhaps as a function of time as it varies, or as a function of wavelength across different parts of the optical band or the electromagnetic spectrum. A third would be astrometry, to measure the precise position of an object relative to some other object, or even to measure the motion of a nearby object, such as an asteroid. Finally, sometimes we just want to take a pretty picture, whether that be for public relations purposes or to remind ourselves why we do what we do. An optical imager is constructed in the following way. A detector, which records the image, is placed inside an instrument behind a telescope which collects the light. This records the raw image to a computer where it is stored for later processing. While this raw image can often be viewed directly, and this is useful for some purposes, there are always imperfections in practice. There can be unwanted signals, defects or patterns associated with the detector, distortions, gaps in the image, artifacts, and so on, and it is not calibrated. We want to remove and correct these issues in order to produce an accurate image of the sky that is usable for science, and we call this process image reduction. I demonstrate this with the following image here at left, which shows a raw image taken by a particular detector, in this case a near-infrared detector. While you can clearly see that this is an image and that it contains observations of stars and even a galaxy at the center of the field, it also contains many unwanted signals and artifacts associated with the detector itself that we want to remove to make this usable for science. Or in other words, we want to convert an image like this, which is dominated by these artifacts, to a nice image like this, which is then usable for data analysis at later stages. This lecture will be broken into two components. For the first part, I will talk about the technologies that we use to collect optical imaging, including basic telescope and optical filters, the detectors that we use, and how the images are stored in software. In the second part of the lecture, I will talk about the processing steps that we use to reduce the raw images to produce science-usable images. In particular, bias subtraction, flat fielding, and astrometric registration and coaddition. There are additional steps that are sometimes necessary that I won't describe in this lecture, but will make available separately online. Almost all professional telescopes are of a reflecting design. In the simplest case, the incoming light is reflected off a primary mirror, which is usually very large, meters in diameter, sent to a secondary mirror, which is much smaller, and this focuses the light onto a focal plane where the detector is placed to record the in-focus image. Usually, although not always, somewhere within this beam, an optical filter is placed to limit the transmitted light from the whole optical spectrum to a standardized passband. There are two common sets of filters that are employed within optical astronomy. The Sloan filter set containing the U, G, R, I, and Z filters. Each has a specific transmission curve focused on a different part of the optical spectrum. For example, the U band, which restricts light to the near ultraviolet, the G band, which restricts to bluer light, or the I and Z bands, which are for near infrared light. There are also the other systems, such as the Johnson-Cousins filter system, shown here, as well as many others. There are also separate filter systems for the near infrared and the ultraviolet. A detector is placed at the focal plane to record and digitize the image. Essentially, all modern detectors, whether that be in the optical near infrared or the ultraviolet, are based on a common physical effect known as the photoelectric effect, which allows photons that strike the detector to be converted into free electrons, usually by providing energy to free an electron in some sort of semiconductor ground state to a conduction band state where it is able to move freely. The efficiency at which a detector is able to do this is called the quantum efficiency. It tells you for each photon on average that strikes a detector, what is the probability that that photon will actually produce an electron that is free to be manipulated by the detector. Most modern astronomical detectors in the optical are very efficient, approaching 100% at the wavelength to which they're best optimized to observe. However, depending on exactly how the detector is designed and how it's optimized, the quantum efficiency will usually fall off towards other wavelengths. So for example, the green curve here shows that the quantum efficiency as a function of wavelength for a rather typical optical detector, peaking around 90% in the middle of the visible range, but declining towards the ultraviolet and towards the near infrared. The blue and red curve show different designs of CCDs detectors that are better optimized for detecting blue light or for detecting red light. Now, to actually record an image, we need more than just a single detector element. We need many, many, many. In fact, we need millions of them. So each of these elements, usually we have a detector that is gridded into a rectangular array of these elements, each of which is called a pixel. And the detector will be composed of millions of them. So for example, for a fairly basic, relatively small detector, it might have 2,000 pixels in each dimension. The product of that adds up to 4 million pixels. And the photoelectrons collected by each pixel during an astronomical observation must be separately stored as the observation is being taken, transmitted if necessary, amplified to a point where they are detectable and not just single particles, counted, and then eventually recorded on our computer system. And so this is quite a large task. The preeminent system to do this, and the most widely used technology, is called the charge-coupled device, which began widespread use in the 1980s, and it's abbreviated as a CCD. And an example of a CCD is shown here. And this is used ubiquitously in optical astronomy. It is not the only technology. There are other types of detectors that are also used in the optical, and in the near infrared, a completely different system is used. However, all of them use a common data processing system, and so the techniques that I will describe later on in this lecture will be applicable to all types of optical and near infrared imager. A CCD is designed as follows. A silicon wafer is imprinted with a large number of tiny electrodes that can apply voltages to different parts of the detector. These voltages can be set in such a way that as electrons are built up and collected over the course of an exposure, they can be held in place such that by applying voltages such that they cannot move between where they are collected and other pixels in the device. This same system allows us to move the charges around when we're ready for it by manipulating these voltages to enable the charges to be moved, for example, from here. By changing the voltage, they can then be moved over here to the right, and so on, to move them anywhere that we want in the array. This allows us to have only a single amplifier system, because this is the most expensive part of the device, to register millions of different pixels. And this is cheap, stable, and reliable, and this is why CCDs are so ubiquitous in the subject. The way this works is often analogized as a bucket brigade. In this analogy, each pixel on the device can be thought of as a bucket that collects raindrops during a rainstorm. The rainstorm begins when the shutter in front of the detector opens to the night sky, and photons begin to stream in through the telescope onto each pixel on the device. The buckets containing the rainwater held by as the signal accumulates, slowly build up until the exposure ends. At that point, the shutter closes, the rainstorm stops, and the charge, or the water in this analogy, is moved around the detector in a specific sequence such that eventually each signal element reaches the amplifier one by one and is recorded as appropriate. This is best shown in a simple animation, which I show here. In this case, we have a simple 5x5 detector with signal indicated by the intensity of this grayscale map. We have our actual imaging detector here. We have a serial array here at the edge. And once the exposure has been completed, it reads out in the following manner. So each column is read out to the serial array, and then each row within the column is registered one at a time. And so one by one, each pixel in the array is read individually by the amplifier system, which is over here at the bottom right. How does this actually get recorded? So each time a pixel charge packet reaches the amplifier, the electrons within that packet, which are a very small number of electrons initially, are amplified to become a much larger amount of charge. And the voltage that that accumulated charge produces can then be recorded using a voltage measuring system. That amount of voltage is then stored back from this analog format to a digital format again in the computer in units of counts, or as they're frequently referred to, ADUs, analog to digital units. The number of ADUs registered per electron, so electron to voltage back to ADUs, is known as a gain, and the reciprocal of that value is the inverse gain. So the inverse gain tells you for each ADU in your raw output image, how many electrons were responsible for producing it. Usually, this value is set close to 1, such that a value of 10 in your detector corresponds to approximately 10 collected elements in that pixel. However, it's rarely exactly equal to 1. In addition to this real astronomical signal, which can come from sources beyond the Earth, but also the emission from the night sky itself, there are other signals to be aware of. The most important of which is the bias signal. So the voltage that is present within the amplifier, even in the absence of any signal, is not necessarily 0. Usually there is some baseline voltage known as a bias voltage that is ever present. And so as a result, even if there is no signal there to be read out, there will be some positive signal that exists that must later be subtracted off to get the true amount of astronomical signal. In addition, for certain types of detectors, in particular near-infrared detectors or uncooled optical detectors that are not cooled by liquid nitrogen, there may also be some amount of dark current, which is signal from electrons that have been excited not by photons, but by thermal noise within a detector. However, the dark current can usually be neglected for optical observations in cooled devices. Summing this all up in quantitative terms, the counts or ADUs that are registered by a detector at the end of an observation can be described by the following equation for each pixel within a device. If the true intrinsic photon rate in photons per second striking a pixel is quantified as P sub xy, and the number of seconds that we hold the shutter open is quantified by the value T, the number of counts that we will get is the product of those two values multiplied by the quantum efficiency, which describes how many of those photons actually produce electrons, added to the dark current value, which is usually 0 for the optical, divided by the inverse gain, which describes the conversion to from actual electrons to output units, and then finally added to the bias voltage. This ignores noise. Of course, in reality, we're subject to fluctuations due to counting statistics. And so for weak signals, that can cause significant fluctuations in this. But for many exposures added together or for strong signals, this can be neglected. There's one other effect that I have not described, which is linearity and saturation. So a good CCD is linear over a very wide regime, such that if you double the incident photon flux on a pixel, you will double the ADUs that the device registers at the end. And this is usually the case. However, there are regimes where it becomes no longer the case. In particular, at very, very high count levels, the CCD will encounter saturation. There are two versions of saturation. The one that is usually encountered first is digitizer saturation. And this describes what happens when the number of electrons being sent to the amplifier and then onto the detector is above the value that can actually be recorded by the system. This usually occurs at this binary value of 2 to the 16th power, or 65,536, where you have, if you have more than that number of ADUs, the value will be recorded as this maximum value and not the true higher value that is the real amount of signal that is being recorded. There's another type of saturation that is also sometimes encountered, which is a property of the pixel itself, known as full well saturation, which is what happens when the number of electrons being stored in a pixel during the exposure exceeds what the pixel can actually hold in place. And in many cases, not only can the pixel not only record any more electrons, but those additional electrons will spill over into neighboring pixels, producing large-scale artifacts such as the types that you see here, which is known as blooming. Fortunately, because this only affects the brightest stars, or the pixels close to or along the same columns as brightest stars, usually we can simply exclude the affected pixels from our later analysis and not actually have to worry about correcting for it. Finally, once the signal has been appropriately transferred and amplified and digitized, we need to store it in software. The convention for storing it is established by the FITS format, which is common both to optical and actually other wavelengths as well, and in fact, even beyond astronomy. And FITS stands for the Flexible Image Transport System. A FITS file has two components: a header, which stores metadata associated with the observation, such as the position on the sky, the name of the object being observed, the filter that is within the beam, the name of the observer and the name of the observatory, and various other bits of information that you may want to know. It's stored at the start of the file in simple plain text. The second component is the image data, the value associated with each pixel in ADUs, which is usually a 2D binary array in the case of optical imaging, although for other wavelengths can take different formats. FITS files can also have extensions to allow many images to be stored together in a single file, which is useful, for example, for instruments that have multiple amplifiers or even multiple CCDs. An example of this is shown here. On the left, we have the header showing a variety of keywords describing various aspects of the observation and the values associated with each of those keywords, and sometimes also some comments helping you interpret what those values mean. Then on the right, we show the image itself as a 2D array of intensity values. So this is the end of the first part of this lecture. So I'll stop here and pose a few questions for you. At this point, you're free to pause the lecture and refer back to earlier parts of the lecture if necessary to answer these. The first question is, what makes CCDs so useful for optical astronomy? The second question is, what are the three most important elements in the sensitivity equation? What does each refer to, and what are the units of each? And the third question is, what are the two components of a FITS file? So I'll now move on to the second part of this lecture, which describes the steps that we take in practice to convert raw images to usable science images. In other words, image reduction. So after a night of observing, we will likely have a large number of FITS images containing both the science images of the source or sources of interest that we want to understand, as well as the raw calibration data that was taken at the start of the night or the end of the night. So the basic task that confronts us is to convert the raw science images together with the calibration images to a series of reduced FITS images, such that for these reduced images, for each pixel within each image, we can determine the sky brightness at that location on the sky at that time, and also the celestial location associated with each pixel in terms of right ascension and declination. The basic steps of this are as follows. We have to remove the bias signal, and that's known as bias subtraction. We have to calibrate the different relative sensitivities of each pixel and each part of the detector relative to each other. That is known as flat fielding. And then we have to register the positions of each pixel on the sky, and if we have multiple exposures, combine them together. So the first step is bias subtraction. As I've already mentioned, CCD data will contain a bias signal that must be removed before further processing. So this can be visualized here, where we have an image of a part of the sky. And in part of this image, which has been exposed to the night sky, you can both see a baseline value associated with atmospheric emission from scattered light by the atmosphere, as well as background zodiacal light and air glow from the night sky itself, superimposed with signals from stars and galaxies. However, part of the image here you can see was not actually exposed to the sky and looks much darker, but the amount of signal associated with this region of the detector is not actually zero. For example, if we draw a profile through the image, we can see that the actual pixel value here, rather than being 0, is actually around 1,000, and so that's known as the bias level. The region that is exposed to the night sky has a higher value, but the actual numbers associated with that is still the sum of the real sky background and this bias level. And we have to remove that bias level before this data can be used for further processing. So how do we do this in practice? There's two methods. The one that is most typically used is to take bias calibration images. So usually during the afternoon, before the sky has actually gotten dark, we keep the dome closed, we turn off all the lights, we close the shutter in front of the detector, and we take a series of calibration 0-second exposures. We then average those together and take the value of each pixel to measure the associated bias value of each pixel. Once that has been done, we have a master bias image that can be subtracted from all our other images that have actual signal within them to measure or to remove the bias from them. An alternative method is to overscan the CCD during the other exposures by continuing to read out the array even after the astronomical signal has been cleared, which allows us to measure a common bias value for the detector as a whole. To visualize the basic method, this is shown here in a case where the actual amount of bias does vary from pixel to pixel in the image. So at left, we have a raw image that is read off by a particular detector, which contains both the night sky, the astronomical sources, but also the bias signal. In the center here, I show an example of a bias image, a 0-second exposure taken under totally dark conditions, which, as you can see, does contain some signal. There's a hot column over here on the left, and there's a little bit of a gradient over here on the right. We want to remove that signal by taking a number of exposures under these conditions, averaging them together, and then subtracting the result from this image. And the effect of that can then be seen over here at the right, where this hot column has been largely removed, as has the gradient over on the right side of the image, producing a processed image for which the signal is only coming from outside the telescope. So that's the first step, but we're not quite done yet because not every pixel in the array actually has equal sensitivity. This can be intrinsic to the pixels as a result of varying quantum efficiency from pixel to pixel. And it can also be the result of obstructions within the optics. For example, dust particles, either on the CCD itself or elsewhere within the optical system. For example, as shown here, there are some particles on the CCD and also some ring effects as a result of dust on the filter. And it can also result from other obstructions or artifacts. And we want to remove these before conducting any science analysis on the image. We do this using a method known as flat fielding. Essentially, we point the telescope at a region of the sky or another reference source that is known to be very close to flat. The true intensity as a function of position is the same at each location. There are two ways to do this. The first method is using a flat screen within the telescope dome, or perhaps even within the instrument itself. That's known as a dome flat. This is usually a white screen that's mounted at the dome and illuminated by an incandescent or halogen or some other sort of lamp. The advantage of this method is that we can take the data in daytime when we're not in a hurry, and we can control the light level by adjusting the intensity of the lamp to make it the appropriate amount of signal for calibration. The disadvantage is that this usually does not result in a perfectly uniform image, and the spectrum is going to be different from what our actual science exposures will have because it's coming from some sort of lamp, which is often in particular quite red and lacks a UV signal and is often not usable at all, for example, for the U-band. The other type of source that we can use is the night sky itself, or more specifically the twilight sky, which still contains scattered light from the setting sun in large amounts, but not so large that they actually saturate the detector. Compared to a dome flat, this is much closer to uniform illumination and has a broader spectrum, including some ultraviolet signal. The disadvantage is that it's still not a very good approximation of what the actual night sky spectrum looks like. And furthermore, the levels vary rapidly with time as the sun sets. And we only have a short window to collect this data before it gets too dark and we no longer have enough sky signal to be usable. Furthermore, in addition to the skylight, we will also have background star and galaxy light, which contaminates our calibration measurements and must be removed if we want this to be actually usable for calibration. A related technique is known as a super sky flat, which is even better than a twilight sky flat, where we actually do use nighttime observations, but use a very, very large number of them to provide enough signal and to remove the unavoidable stars and galaxies, which I won't talk about in this lecture. So regardless of whether we're using dome flats or whether we're using twilight flats, we will usually take a large number of them, and each flat field must be in the same filter as the science observations that we're planning to process with it. We will first, after collecting each exposure, we will bias subtract it. Following bias subtraction, we will normalize each exposure such that it has a median of 1. This is to adjust for any variations in intensity as a result of varying levels of twilight or possible varying levels of intensity from our lamp. Once they've been normalized together, we will combine them, usually using a median average, which is more robust than other types of averaging in case there are cosmic rays or other sorts of unwanted sources in individual images. After that, we will have a master flat combined of all the observations in the same filter. And then we can divide each science image after bias subtraction by that master flat to produce a processed and nearly science-ready individual image. This is demonstrated by the following series of images. At left, we have an example of a particular science image which has been bias subtracted, but not yet flat fielded. While you can see this has a large number of astronomical sources within it, you can also see a variety of instrumental artifacts, such as dust rings, very visible in various places, detector problems here, such as the streak and these horizontal streaks across the image. The flat field is shown here in the middle, which shows all the same artifacts and allows us to quantify the variation in sensitivity of each pixel as a function of position within the detector. And by dividing the bias-subtracted science image by this flat field, we can remove all of these intensity variations, as well as the broader variation across the field, to produce a nice flattened science image, where, as we expect, the sky level is approximately the same across every pixel. It hasn't removed every artifact. We'll come back to that later, but it's certainly an improvement over the unflat fielded image. So the next step is coaddition. So we often take several repeated images of the same source in sequence. There's a variety of reasons why we might do this. One of them is that if there are bright sources that we actually care about, but also faint sources that require a lot of exposure time, if we take a number of exposures and average them, we avoid the risk of saturating the bright sources because we can read them out before they reach the saturation level. This also allows us to mitigate certain types of artifacts because those artifacts may not be present at the same location in every image. And so by averaging them, we can essentially flush out the bad measurements with the good ones at the same position. If the telescope was not moved between exposures to a very high level of precision within about a pixel, this is quite simple. We simply add, or more likely median average, these in software. If the telescope was moved, however, we have to quantify and correct for this by measuring the relative offsets between each image, by measuring the position of some sort of reference star or stars within the image, and then shift them appropriately before combining. So an example of this is shown as follows. We have 3 images of the same general region of the sky, but the telescope has been moved slightly from image to image using a technique known as dithering, so that the positions of the stars and galaxies within the image is actually slightly different within each one. By combining the 3 images together after being appropriately aligned and taking a median average, the image becomes deeper because we're using 3 times as much signal. And using the median averaging technique, we can also remove some of these column artifacts that you can see to produce a nice cleaned up, deeper image, at least within the part of the field where all 3 images are on that part of the sky. So how do we do this quantitatively, and how do we absolutely calibrate the image such that a given position in terms of pixels on the image can be translated to a right ascension and declination that can be globally be interpreted? So this is done using information within the FITS header. There's a series of standard FITS keywords that encode the translation equation between any pixel or even any subpixel within the image to a right ascension and declination value. There are a variety of conventions for doing this, but the convention for the simplest case, where the translation can be expressed as a linear equation, is given by the following set of keywords. There are 2 keywords that describe the reference pixel. These are arbitrary and can be chosen by us, so they're not actually broadly meaningful and don't need to be solved for because we can choose them. Usually we choose values of pixels towards the center of the array, of the pixel array. The values that we have to solve for are the following 6 values. 4 of them are the transformation matrix, or the CD matrix, which encodes the size of each pixel in arc seconds, the shape of each pixel, whether it's square or perhaps might be a little bit rectangular, and the rotation of the field on the sky, whether it's oriented with north up or in some other orientation. Then there are 2 values which encode the pointing location, which is to say the right ascension and the declination of these reference pixels. Additionally, there are some standard text keywords which explain this sky projection to turn this linear equation into the spherical coordinates on the sky. How do we actually solve for these values in practice? So we have to select at least 2 stars in the image which have been correctly matched to catalog values. So the X and Y positions of 2 stars and the right ascension and declination positions of those same stars within the catalog, which gives us the sufficient number of values to solve the equation to derive the 6 astrometric parameters that we need to know. After solving for those equations, we can determine these parameters and simply write them to the fits header. And after that's been done, any astronomical software that you use, whether that be a visualization software like DS9 or a command line software like Python, can then be used to translate X and Y to right ascension and declination, or vice versa, anywhere in the image. In the end, we will be able to therefore be able to explore an image and translate any position within it to determine its right ascension and declination. And we'll do this in practice during the upcoming Python exercises. So to summarize, basic CCD reduction boils to 3 basic steps. The first is we remove the unwanted bias signal via bias subtraction. The second is to calibrate the relative response of each pixel using flat fielding. And then finally, we align our images with each other and calibrate against the global sky coordinate system via astrometric registration and coaddition. With these basic steps, you can produce images from essentially any optical telescope in the world, even with your own homebrew software from scratch. And it's relatively straightforward. So before I continue on with the conclusion and summary, I'll once again pose a few review questions for you. So if you'd like to pause the lecture at this point and make sure you understand the answers to this question, I'd highly encourage that. So the first question, do bias calibrations have to be taken in the same filter as your science data, and why or why not? What about flat field observations? Do those need to be taken in the same filter as the corresponding science data that you process them with? Second, would it be okay to reverse the order of operations and divide by the flat field before you subtract off the bias? And why or why not? Third, why do we need 2 matched stars to register an image's astronomy versus the global coordinate grid? Why not just 1? And then finally, why do we tend to use median combinations in these steps rather than a simple arithmetic mean? All right, so before I continue on to my conclusions, I do want to stress that while I've presented the basic steps here, this does not describe every step that necessarily needs to be conducted in practice under all circumstances. Often, many other things may need to be done. For example, you may need to directly mask the bad or unexposed pixels in the array rather than simply rely on median averaging. You may need to subtract that dark current that we brought up and said was usually negligible, because it isn't always. In particular, in the near infrared, it is not negligible and needs to be subtracted. You may need to correct for nonlinearity in the system. You may need to correct for charge transfer losses, where photoelectrons get left behind by a pixel or 2 as they are transferred across the array towards the amplifier. You may need to subtract the night sky background, either to correct for fringing effects or because the night sky is rapidly varying. You may need to remove cosmic rays signals. And frequently, you may need to correct for astrometric distortions, nonlinearities in the solution that connects the X and Y coordinates to right ascension and declination. These steps may not always be necessary, but often they are. The key to understand is to understand your instrument and observing mode and consider what your actual science needs are, so you know what steps you must do, because some of them are very time-consuming, and what you can skip. If the image looks bad when you've carried out these processes, it is often a signal that something is wrong. And one element of practical advice that I'd certainly like to impress upon everybody is that if your image at the end of your reduction does not look right, it probably means that you can't trust photometry and you may need to try again, and you may need to try more advanced techniques. And so I'd encourage everyone, in addition to viewing this basic lecture, to also look at the supplementary lecture on these advanced methods. That concludes this lecture. I'm looking forward to seeing this year's participants soon in the hands-on Python sessions for both follow-up discussion and a reduction of some real images in practice that we'll do in the session. This lecture and all lectures in this school will be made available to everyone on our website after the school concludes. So you can go to this lecture, the URL of which is given here, to access these resources. And please feel free to share them with your friends and colleagues. Thanks for watching.